In this paper, we propose a wavelet-based codec to enable high frame rate transfer and display of high-resolution 360-degree videos. 360-degree videos allow users to explore a scene while the camera moves along a pre-recorded trajectory. This type of richer media allows, for example, to enhance the immersion of VR experiences and gives the user more control. The part of the video that is displayed in the viewport is only a fraction of the entire 360-degree sphere. Therefore, 360-degree videos require high resolution to allow for the result of cropping and retargeting the scene to the smaller viewport to remain visually appealing. It is still common practice to use the same codecs for encoding 360-degree videos as for traditional videos. However, these codecs do not allow to load and decode arbitrary parts of the frames independently because their discrete cosine transform follows a non-regular grid. Thus, usually the entire frame is decoded, while only a fraction of the data is actually used for rendering. In this paper, we want to shift the focus to another method of data coding, the wavelet transform. Using a wavelet transform as the basis for a codec has two decisive advantages. Firstly, any areas of the frame can be loaded and decoded independently of one another. Secondly, the image is decoded over multiple frequency levels. This way, the target resolution in single areas can be chosen to be lower in favor of speed. We will use this principle later to introduce foveated decoding, where the resolution decreases with the distance from the viewpoint. In order to practically evaluate wavelets for 360-degree videos, we have implemented a codec based on wavelet compression. To our knowledge, this is the first wavelet-based approach of a video codec for 360-degree videos. For the transform of the single frames, our codec uses a 2D fast wavelet transform based on the CDF97 wavelet, which offers a high-quality reconstruction of natural images. The transform is performed over a defined number of levels, which hold the respective frequency information of the frame. Also, the interframe compression is defined as another one-dimensional wavelet transform applied to the frame-wise transformed wavelet representations. The focus of our codec is on the reconstruction speed and quality of the video. As any other form of video compression, some information needs to be discarded. The choice of which wavelets are dropped during the compression depends on several factors, for example, their intensity, frequency level, and position on the zenith. During playback, only the field of view of the viewport is loaded and decoded, allowing us to achieve significant bandwidth savings. Each layer of the wavelet transform represents a lower resolution version of the frame. We utilize this concept to display the foveated area in full resolution using eye tracking, with the quality decreasing from the focal point. We call this method foveated decoding because the decoding load is reduced with the technique applied. With the discrete cosine transform, a comparable approach cannot be implemented in a straightforward manner. The foveated decoding is optional in our codec. For the evaluation, we consider 360-degree videos with static camera as well as videos with moving camera trajectories. The evaluation is performed against the established codecs HEVC and AV1, as well as in relation to previous work. Our analysis shows that our codec can achieve comparable quality, but at a significantly higher decoding speed. Our experiments are run without foveated decoding and reconstruct the entire viewpoint in an equal quality. With our foveated decoding applied, the speed increases again significantly. Here you can see a comparison in terms of image quality. In conclusion, wavelet-based codecs have great potential for use on 360-degree videos. While the quality is on par with popular codecs, our codec achieves significantly higher reconstruction speeds. This is accomplished by optimization and exploitation of the properties of the wavelet transform.